All right, hello everybody. So this week we're going to be, or not this week, in this video we're going to be covering chapter 4.6, which is on modeling with exponential functions. All right. So basically we're just going to go over a couple different ways that we can use the exponential function to model things, and look at some specific examples. All right. So the first thing that we're going to look at is when we're talking about exponential growth. All right. So the standard formula for exponential growth, or an exponential growth function, is we're going to take n of t, which is our population at time t, right? And that is going to be equal to n, that's a w, not an n. What have I done? All right, so we're taking n naught, which is our initial population, and then we're going to multiply that by e to the power of rt, where that r right up here, that is going to be our relative rate of growth. All right? So this is fairly straightforward, right? We're just taking the relative rate of growth, e to the rt, and we're multiplying it by that initial population to get our population at some time t. You'll notice that this right here is pretty much the same formula that we were using in when we were talking about continuously compounded interest, and that's because it's derived in pretty much the same way, right? So yeah, let's talk about this relative rate of growth here for a second. So sometimes this will just be given to us, what the relative rate of growth is, and other times we're going to have to find it. Okay. So kind of the neat thing about how we can go about finding that is first of all, we of course have to identify that the situation we're looking at has this sort of exponential growth happening. But once we've done that, then we can write the equation and fill in all of the blanks that we don't know, and then solve for what that relative rate of growth is going to be. So let's look at an example where we can do that. So let's say that we have a population of, let's say 200 rabbits. Right? They're on a little island somewhere, and we want to model the growth of the growth of these 200 rabbits over time. Okay? And we're going to say that every 3 months, the population size doubles. Okay? So this was something that Tim was talking about in his videos last week when he was just talking about exponential functions, right? And essentially what that can tell us is that if we have our function, right, we know that these rabbits are going to be growing exponentially, right? The more rabbits you have, the more rabbits you get. So we can write our n of t is going to be equal to our initial population, NO, which is going to be 200 in this case, times that e to the rt, right? And we want to figure out what r is going to make this equation true and actually model the situation we've been talking about, right? And we're going to let, also, t is measured in months, okay? Just so we're all on the same page about the units that we're using, right? So t is measured in months, and we know that after 3 months, right, our population size is going to double. So what we can do here is we can take our n of 3, and we know that's going to be equal to 400, right? Twice the initial population. So when we take that, we get 400 is going to be equal to 200 times that e to the power of r times 3, right? The number of months that has lapsed since that size is doubled, right? And then we can take our 400, we can divide the 200 on both sides. Excuse me, I'm sorry. And then we will get that we have 2 is going to be equal to e to the power of r times 3, right? And then we can take the natural log of both sides of our equation here, and we will get that the natural log of 2 is going to be equal to r times 3. And then we divide that 3 by both sides to finally get that the natural log of 2 over 3 is going to be our r. Okay? So when we finally write this all out, we get a function for modeling the growth of rabbits on this island is going to be 200, that initial population, times e to the power of the natural log of 2 over 3 times t. Right? So we take any number of months that we want, we plug that into our equation, and we solve for that value, and we'll figure out how many rabbits are going to be on this island after that many months. Okay? Fairly straightforward. And we can use this model that we've created to answer different questions about it, right? Like, say we wanted to know when are we going to get to 1,000 rabbits, right? We just set n of t to 1,000, and then we can then solve for our t. Okay. This one is fairly similar to the kinds of things that we were doing last week, but we can also talk about a different kind of model. In this case, radioactive decay. Right. So if we have a radioactive material, right, it's going to have what we call a half-life. Okay, so this is just the time that it takes for half of that material to decay. Okay, so when we're looking at the equation that, or the function that we're going to be using to model radioactive decay, in general, it's going to look something like this. So we take our m of t, which is going to be our mass at time t, right, mass, that will be equal to our initial mass, and then we'll multiply that by e to the power of negative RH, and in this case, oh, I'm sorry, it's not supposed to be an H. That is a T. In this case, our R is going to be equal to the natural log of 2 divided by H, where H is the half-life of our material. Right? So we can figure out that this R is supposed to be the natural log of 2 over H in a very similar way to how we found this natural log of 2 over 3 for our increase, right? Our exponential growth function. However, in this case, I'm just going to skip over that proof and just let you know that it's going to be R is equal to the natural log of 2, right? So, or the natural log of 2 over H, right? So once again, this is very similar, right, to the case that we were talking about before, right? We were talking about exponential growth, because the rate of growth, right, is going to depend on the mass or the size of the initial thing. In this case over here, radioactive decay, right, the amount that's being decayed is going to depend on how much of the material is there, right? So they're very similar. This is just, a downward. We're decaying instead of increasing, right? Yeah. So I'm going to next go on and just tell you about one more sort of law that we can look at, one more function with blanks that we can fill in, and that's going to be the law of cooling. And this is Newton's law. All right. So Newton's law of cooling, we're going to take T of T, right? And this is going to be the temperature of an object. And that is going to be equal to T of S. T of S we're going to define to be the temperature of the room that we are in, right? So it doesn't necessarily have to be a room, right? It could just be, it's just the ambient temperature of the space around the object we're talking about, right? We're going to add to that dO, and this is going to be our initial difference in temperature between the object and the surrounding space, and this is going to be equal to E negative KT, and this K is just a constant that depends on object, right? So different objects have different constants of cooling that's going to affect how we increase and decrease. Okay, so I'm I'm not really going to explain why this is true. However, we can take a look at like different values that this is going to take and just try and convince ourselves that this makes sense as an equation modeling the cooling of an object. Okay, so we're going to take the first temperature that we're going to, or the first time, sorry, the first value of the function that we want to look at. We're just going to look at when t is equal to 0, right? So if we let t equal 0, then t of 0, right? So this is when we first set the object down in the room, right? When we first introduce it to the ambient space so that the cooling takes place. Then that's going to be equal to Ts plus d0 times e to the power of 0, right? E to the power of 0, just like anything else, that'll leave us with just a 1 there. And so our whole T of 0 is just the temperature of the room, and then plus the difference, the initial difference in the temperature between the object and the room, which is just the temperature of the object. And this is initial, right? This is the initial temperature of the object, because obviously that's going to change, right? So that makes sense. When we first set the object down in the room, right, the initial temperature should be the initial temperature of the object. So, whoops, sorry about that. So that makes sense, right? If instead we're going to look at our limit as t goes to infinity, right, of our T of t, we want to look at what's going to happen if we just leave the coffee cup or the object in the room for a really long time and see what happens to its temperature, right? So if we do that, this T of S, we're not going to be affected at all. We're going to get that plus D0, but then let's take a look at e to the negative KT, right? What's going to happen to that value as we let t get really, really, really large, right? Well, we're going to have e raised to the power of a really large negative number, which means that as we let that t go to infinity, we're going to get a 0 here, right? Which just leaves us with the temperature of the room. So if you leave an object in a room for a really long time, eventually the object will become the same temperature as the room that it's in. Okay? So let's take a look at this and try and model a situation, right? So I'm going to say, so let's model. I'm going to take a soda out of the fridge, and place it on the counter. So excuse me. So T of S in this situation, we're just going to say is going to be 70 degrees. All right. Just keep my house at a fairly normal temperature, right? Just a nice 70 degrees, not too hot, not too cold, right? And our soda, because it's fresh out of the freezer, its initial temp is going to be 40 degrees. And these are both in Fahrenheit, my apologies. All right? Which means that our D0, right, is going to be the difference in temperature between the object that we're taking out and the temperature of the room. Okay? Which is just going to give us 30 degrees Fahrenheit. All right? And once again, I'm just kind of making this up here. We're going to say that 1 hour, right? So at T equals 1 hour, the temperature of the of the soda will be, let's say it gets up to 60 degrees Fahrenheit. Okay? So we can write up all of this information that we have here, right, into our equation. So T of T is going to be equal to our T of S, or the initial, or the temperature of the room, right? So in this case, 70 degrees Fahrenheit. And then we're adding that initial difference in temperature, which in this case is negative, apologies again, negative 30 degrees Fahrenheit. And then we're taking it to e to the power of negative kt, right? So now we want to figure out what the value of that k is for this imaginary situation that I've created, right? And so we're going to let T of 1 be equal to 60 in this situation, right? So our 60 degrees Fahrenheit will be equal to 70 degrees Fahrenheit minus 30 degrees times that e to the negative k, and then we have a 1 there. All right? So we subtract the 70 degrees from both sides to get a negative 10, and then we can divide the negative 30 by both sides, which is going to just be our 1/3, and that is going to be equal to our negative k, e to the negative k. Right? We want to take the natural log of both sides of this equation, so we're going to get the natural log of 1/3, and that's going to be equal to our negative k constant, right? And the last thing that we want to do in order to simplify this is we multiply both sides by negative 1, right? So we get negative natural log of 1/3 is going to be equal to our k. And although I realized that I just said that was our final step in simplifying, there is one more thing that we want to do. 1/3, right, is going to be equal to 3 to the power of negative 1. And so we can take this negative 1 and multiply it outside of our exponent. So we're actually just going to get negative, the natural log of 3, right? So just positive is equal to our value k. All right? Very good. So we know that by our law of cooling, for, once again, this all these numbers are made up, right? I don't actually know if this is how long it takes for my soda to cool in that temperature of a room, but we can take, or heat up, right? Warm up. We got 70 degrees Fahrenheit minus 30 degrees Fahrenheit times e to the power of negative natural log of 3 times t. All right? and that is going to be the function that models the time it takes for, or the time it takes for my bottle of soda to heat up. All right, and so we can say that I'm not willing to drink my soda anymore after it's 50 degrees Fahrenheit, right? So let's say that we want to find the time. Soda is 50 degrees, right? Because after that, I don't want to drink it anymore, so I want to make sure I drink it before that 50 degrees happens, right? So we want to find the t value, right, such that t of t is equal to 50 degrees Fahrenheit, right? So we take 50 degrees Fahrenheit, set that equal to our 70 degrees Fahrenheit. We subtract the 30 degrees, we multiply by e to the power of the natural log of 3 times t, right? So then we just want to find our t value, right? So we'll start by subtracting that 70 from both sides, and then we'll divide both sides by that negative 30, sort of like we were doing before, right? And that's just going to be equal to e to the power of the natural log of 3t. All right. So we're going to get 1/10. What am I doing? I don't know why I just said that. Oh my gosh. I'm messing up all over the place. All right. So we're going to get our 2/3 over here. And we can simplify our e to the power of e to the negative natural log of 3t, right, is actually just going to be 3 to the power of negative t, right? So then we can take our log base 3 of 2/3 is going to equal negative t. So we'll get log the negative out front, base 3 of 2/3 equals t, which we can also write as log base 3 of 3/2, right? Using the same trick that we used before. That's going to be equal to t. And then we can also do one more step here, right? Because since we have division on the inside, we can break that up into base 3 of 2, right? And log base 3 of 3 is just going to be 1, so we get 1 minus the log base 3 of 2 is going to equal our time, all right? So that's going to be the amount of time, right, measured in hours that it's going to take for our drink to get to a point where I don't want to drink anymore. So got to make sure I drink it before 1 minus log 3 of 2 minutes. All right? So yeah, that's everything for this video. That kind of wraps up section 4.6, right? Just a couple examples of how we can use the exponential function to model different kinds of situations. All right?